Hello, my name is Zhengfu Chen. I'm currently a PhD student in Agricultural and Biological Engineering Department at Purdue University, working with Professor Kinsey Ambrose and Carl Waskrin.
In this video, I will briefly describe the work presented in my recent journal paper entitled Measurements of Green Kernel Friction Coefficients using a Reciprocating Pin Tribometer. The friction coefficient is the ratio of the frictional force to the normal force between two objects. The friction coefficient has a significant effect on grain flow and storage behavior. Thus, it is an important property to consider when designing agricultural equipment like chute, conveyor, and storage bin. In addition, it is a critical input parameter for discrete element method simulations. In the past decades, a variety of friction test methods have been developed to measure the friction coefficients of green kernel, for instance, tilting table test and flat surface sliding test. However, these tests generally use spot grain, which has the potential to roll during testing and affect measurements. A tribometer has been widely used to measuring the coefficient of friction of inorganic materials like metals and ceramics. The main advantages of the tribometer are high data acquisition rate and highly accurate measurements. However, the device has not been used to measure green kernel friction coefficients, since it is challenging to affix green kernel to the device and analyze the data when irregular shape samples are tested. The objective of this study was to explore the use of a reciprocating pin tribometer for measuring the static and dynamic coefficient of friction between green kernels and between kernels and boundaries. Figures in the slide present the test setup of the particle wall friction test to accommodate the irregular shape of green kernels. A top sample holder pin was specially designed and produced with a 3D printer. A single kernel was carefully superglued onto the pin. During the test, the top sample was first lowered vertically until it came into contact with the bottom sample. The downward movement of the top sample stopped when the normal force measured by the load cell reached a specified level. The bottom sample was then moved horizontally by the driving unit. The normal force and tangential force applied to the top sample were measured and recorded by the load cell. The difference between particle wall and interparticle friction test setup is in the bottom samples. For the particle wall friction test, the test material in the form of a circular disc was directly affixed to the bottom sample holder. For the interparticle friction test, green kernels were glued onto a 3D printed plate as bottom sample. MATLAB scripts were written to calculate the static and dynamic friction coefficients from the normal and tangential force measured by the load cell. Typical friction coefficient versus time plots for a particle wall and an interparticle friction test are shown in the slides. For particle wall friction test, friction coefficients can be directly calculated as the ratio of the tangential force to the normal force, while for interparticle friction tests, because the particles are not flat, a coordinate transformation is required when calculating friction coefficients. Data analysis process was specifically developed to calculate dynamic friction coefficients for interparticle interaction. The table in the slide summarizes the friction coefficient values measured in the current study and compared to the values reported in the literature. It is found that the static friction coefficients are larger than the dynamic friction coefficients for all test conditions. The friction coefficients of the corn wall combination are smaller than that of the wheat wall combination. This finding is consistent with expectations, as the pericarp of the wheat kernels, which contains creases and bumps on the surface, is rougher than the pericarp of corn kernels. The data also indicate that for the same type of grain, the coefficient of frictions are larger for the grain steel than for grain acrylic, as the surface of the acrylic disc is smoother. For internal particle friction tests, the results are consistent with the finding obtained from the particle wall friction tests, with corn having a lower value than wheat. In conclusion, particle wall and interparticle static and dynamic friction coefficients of corn and wheat kernels were measured using a reciprocating pin tribometer. The test setup and procedures were adjusted to accommodate tests of irregularly shaped green kernels. A force balance analysis were used to calculate the dynamic friction coefficients when the contact surfaces were not aligned with the moving direction of the bottom sample holder. This study demonstrates the feasibility of using a reciprocating pin tribometer to measure friction coefficients for corn and wheat. The developed test methodology could also be used to measure the friction coefficients for other types of particulate materials with relatively smooth surfaces.